Today we'll be talking about pharmacodynamics, what the drug does to the body. That is, why do we take drug? What is the mechanism of action? That is what we're talking about. Pharmacodynamics. See, when you give a drug, it has to go and attach to a receptors. So that receptors will send some signals, and then its mechanism of action will be continued. So there are 4 types of receptors here. The most basic is the ligand or the ion channel receptor, and then we have the intracellular receptor, we have the enzyme receptors, and we have the G protein coupled receptors. And there are also some non-receptor action like charcoal, mannitol, antacid. These are all, they just by absorbing itself they'll give it an action. Now first let's talk about the ligand gated or the ion channel receptor. Drugs like nicotinic acid, nicotine and 5-HT3 and GABA A blockers, glycine, glutamate, all these things, what happens is once it attaches to the receptor, it will open it's a ligand, so once it is attaching to the channel, it will open the gate so that all the drug will go inside and ions will move by the concentration gradient like sodium, calcium, potassium, chloride, etc. This is ion channel. Intracellular receptors and enzyme receptors. The intracellular receptors, it means that the drug has to go, it has to cross the plasma membrane and it has to go and inside and produce its action. So since it has to cross the cell membrane, it should be first lipid soluble. So that is very important. And then it has to have, the receptors will be present either in the nucleus or the cytoplasm. The receptors that are present in the nucleus are thyroid hormone receptors, estrogens, we have this vitamin A, we have the sex hormones. All these things will have an internuclear receptor. And the cytoplasm, hormones like steroid hormones, vitamin D, all these things will act on the cytoplasm. So yeah, I'll just show you 1 second. Yeah. Okay, so cytoplasmic receptors are steroid hormones, that is glucocorticoids, mineralocorticoids, androgens. And nuclear receptors, as I told you, there's thyroid hormones, there's vitamin A, and there's vitamin D. So these are all the intracellular receptors. We also have the G protein coupled receptors, which I'll talk about right away. And the next is the receptors which has an enzyme property. So receptors which has an enzyme like property, there are 2 types, guanyl cyclase and tyrosine kinase. Guanyl cyclase, what do is they convert GTP to cGMP. So the enzymes that act as receptors as enzymes are ANP and BNP. Yeah, see, if you see ANP and BNP are guanyl cyclase receptors. And then we have the tyrosine kinase, which is nothing but through JAK-STAT pathway they can act. See, once example the insulin and the JAK-STAT pathway or MAP kinase pathway, we have the growth factors, all the EDGF, VEGF and all that, growth hormones, erythropoietin, insulin, prolactin, all these things are there. And then once the insulin binds to the receptor, the dimerization of the receptors will happen, and then the tyrosine kinase will become active and certain proteins are phosphorylated and thus an action is produced. So this is the insulin tyrosine kinase pathway. JAK-STAT pathway, it's the same, more or less the same, prolactin, erythropoietin, growth hormone, INF and interleukin. So all these things are enzymes that act as receptors. Okay, now the last classification is the our G protein coupled receptor. So G protein coupled receptors is 7 gated receptor. So it has to cross like 7 times across the plasma membrane. It is bound, like it is arranged to 7 times across the plasma membrane. It's like a serpentine pattern, and it's a metabotropic receptor. It will amplify the signals that they receive. So what happens is, once the drug is attached, normally at resting state, G protein coupled receptor will be having alpha, beta and gamma. Actually, alpha, beta and gamma, and GDP is bound at resting state. Wait, see, G protein coupled receptor is bound 1, 2, 3, 4, 5, 6, 7. So alpha, beta, gamma are bound to GDP at resting state. And once the drug, see, once the drug comes and binds to the receptor is activated. Now the GDP will be converted to GTP. Now once the GTP is formed, it will dissociate the alpha. The alpha unit can act on adenyl cyclase or phospholipase C. See, if it acts on the adenyl cyclase, what happens is, this adenyl cyclase will convert ATP to CAMP. So increase CAMP, what happens is protein kinase will be converted to kinase, which will phosphorylate a lot of proteins, and the cell will respond to the drug that is given. So this is one way. Another way is phospholipase C. So this was adenyl cyclase and protein kinase and all that. This is phospholipase C, where it will break the phospholipid of the cell membrane, and it will produce phosphoinositol phosphate, which again in turn is formed by inositol triphosphate and diacylglycerol, which what will it do is it will increase the intracellular calcium, which is the third messengers. So all these things are second messengers. See, the G protein coupled receptors of three types: GS, GI and GQ. GS is what can stimulate the adenyl cyclase. GI, it will inhibit the adenyl cyclase, it will inhibit the CAMP. So the second messengers are CAMP and the inositol triphosphate and diacylglycerol. And the GQ, what will it do is it will directly increase the inositol, it will increase the phospholipase C, thereby increasing inositol triphosphate and diacylglycerol. So what are drugs which act through this pathway? So GS, or beta 1, beta 2 and beta 3 agonists or are drugs which act on these receptors, are all GS type of receptors. They will stimulate the G protein coupled receptor, thereby increasing the CAMP, thereby increasing the cell response to drug. And alpha 2 and M2 drugs will inhibit the CAMP. So inhibition action happens, will decrease the CAMP. And GQ or alpha 1 and M1, which acts on which increases the IP3 and diacylglycerol, which increases the third messenger. Now also there's another type where what happens, see, there's another channel called potassium channel. So this is a specialized unit like beta gamma unit. We talked about alpha unit here. The beta gamma unit, what happens, it will go to the cell membrane and it will open the potassium channel. So once the alpha acts like this, the beta gamma will open the potassium channel. So all the potassium, intracellular potassium, is all moving outside. Once it's moving outside, it's called hyperpolarization. This is also known as G protein related inwardly rectifying potassium channels. So GIRK channels. So what other drugs which act by opening the potassium channels are alpha 2 and M2. See, the same thing, alpha 2 and M2 will act like that, and also dopamine and 5-HT1 serotonin on the receptor 1. All these things will act by opening the potassium channels. So this is how it acts. Okay. Okay, next we'll talk about the dose response curve. See, dose response curve, it is basically the amount of the drug which is given, and the concentration of the drug which is given, and the maximal pharmacological effect. See, we have a lot of receptors in the body. So what happens is, once the concentration of the drug increases, the number of receptors that it occupies will also keep increasing. At one point, all the receptors are being accumulated, all the receptors are being bound by the concentration of the drug. Now EC50 is the concentration of the drug at which and this is a point at which maximum pharmacological effect can be produced by a drug. All right. And this is and EC50 is at which it's a concentration of drug at which 50% of the pharmacological effect is being produced. It does not mean the 50% of the receptors that is being activated, it means the 50% of the pharmacological effect that is being produced. So this is EC450. And what do we do with this? The potency of the drug it will talk about the potency of the drug. Now what happens is, if you have this drug A, now there's another drug called B, so this will produce a graph like this. So if you see, what happens is, the concentration of the drug for drug B to produce the 50% of the pharmacological effect is more compared to that of drug A, which means drug A is more potent than that of drug B. So potency, which drug is superior, which brand of drug or which type of drug is superior than the other, we can use it by using this dose response curve. And also efficacy of the drug can also be, we talked about potency. Efficacy is efficacy is with respect to the pharmacological effect is being produced. See, drug A produces high pharmacological effect, whatever it is, even if it is at the same concentration. See, for drug A, I'm giving, for example, if it's 100 mg, at 100 mg, if drug A produces this much effect, at 100 mg, drug B produces only this much. You can see the pharmacological effect is less when compared to that of drug A. So drug A is more efficacious than that of drug B. So this is what is the meaning of dose response curve. So whenever you say a drug is more potent, if you want to say a drug is more potent, means the graph should be more towards the left. And also, if you want to say a drug is more efficacious, it should be more upward, or it should be high above the respective drug. So this is what is called the dose response curve. Alright, now next video we'll talk about the agonist, antagonist.